Okay, so we're going to resume our discussion here this morning and should be able to finish up chapter 20, but we won't go any farther than this today. So just, again, remember our goal for this chapter and the next chapters that we'll be looking at is we want to learn how to construct confidence intervals and do hypothesis tests or tests of significance with in different settings. So we've already looked at one population, we've looked at two samples, we've done one sample, two sample t-tests, and here in chapter 20 we're getting into proportions, looking at proportions. So doing a quick review here, we'll pick back up on page 4 of your notes in just a second here. But just to, so again, here we're looking at, in this chapter, we're looking at a population proportion. So we're going to call that P as our proportion. And the sort of the natural thing to do is to estimate that using the sample proportion. And we're calling that thing P hat. So we're having another hat in there. So then our goal in this chapter, we're going to try to figure out how can we figure out how to make a confidence interval for this thing, and how can we do a hypothesis test, which means we need a test statistic up there. That's kind of where we're going in this chapter. And so on Wednesday we talked about a few things. We defined what we mean by P hat, the sample proportion. If we have a sample from size n from some population, P hat's going to be the number of successes in the sample divided by the total number of things in that sample. Where again, we're going to generically use that language of success, but it might not always be a good thing what we're looking at. And then what we talked about on Wednesday also was that the mean of the sampling distribution for P hat is going to be P. It's going to be the population proportion. And then we have our standard deviation there as well. And taking that one step further, when our sample size is large enough, so once again we're going to be concerned about having a large enough sample, then our sampling distribution for P hat is going to be approximately normal. So we're kind of back in a familiar situation that we know how to deal with. And so when we're thinking about a confidence interval, we're going to, again, our general form here is we're taking an estimate plus or minus some critical value times the standard deviation. We would like our confidence interval to be this thing right here. We have our estimate P hat, adding and subtracting a z star times the standard deviation. But of course, as we discussed, if we're trying to estimate P, note that P is floating around in this formula here, so we can't actually use this thing. So what we'll do instead is we'll estimate the standard deviation. So the standard error here is our estimated standard deviation. Just plugging in P hat for what P was in there, and that's going to give us a formula that we can actually work with. So here is sort of your takeaway from the first part of this chapter here. Our confidence interval is going to be P hat plus or minus a z star times that estimate of the standard deviation, and making sure to note that we are back in the z world here. So with means, we talked about z star, t star. For proportions, you'll always be using a z star. So that's a slight difference in this chapter. Moving along here, so here's sort of a more formal statement of what was on that previous slide, and kind of the main difference here is that I want to make sure the catch here is that we want to use this interval only when there are at least 15 successes and at least 15 failures. So still reviewing here. So this kind of takes us to our conditions page, right? So the general idea with our conditions is that we want to make sure. We want to make sure that it's appropriate to use these procedures that we're talking about, and checking our conditions is kind of the way to say, can I trust the results I get from this procedure? If my conditions check out, yes. If not, well, we should be a little more careful there. So first, same three conditions as we've always had: random sample, small enough, large enough. Random sample and small enough are going to stay the same. The large enough sample changes slightly. We want 15 successes and 15 failures. So we want to make sure that n times our sample proportion is bigger than 15, and n times 1 minus the sample proportion is 15. So here this is my number of successes, and this is my number of failures. Again, sort of generically using the term success and failure. Okay, so that's all review still from last time. Any questions or comments before we jump into actually applying this, doing an example? Feeling okay so far? All right. So to actually try to implement this thing, let's look at the following example. So again, remember at the beginning of the notes last time, so here we are on page 4 of the notes. We're kind of forging ahead now to new stuff. We were talking about this example of smoking habits and socioeconomic status. And so let's go ahead and construct a 90% confidence interval for the true proportion of people in the upper class who smoke. And if you picked out the right numbers from the table, we had, again, we want the proportion of upper class people who smoke. So there were 211 upper class folks in our 2A table there, 51 of which are current smokers. So I think a good way to start on these problems involving a proportion is kind of write out what it is that I'm considering a success in this case. So just to be very clear, we'll say that a success here is being a smoker from the upper class. So that's kind of we want to look at folks who are in the upper class, and then we want to look at the proportion of those who are smokers. So that's kind of what we're defining as a success here in this example. And what do I need to do before I jump into calculations? Check conditions, right? That's absolutely right. So just make sure that our conditions check out before we forge ahead with calculating this interval. So our conditions, we have the usual 3, random sample, small enough and large enough. So again, the first two are going to kind of be the same as they've always been. How are we doing with the random sample here? Stated in the problem, absolutely, yes. So yes, it's stated. Okay, good there. Small enough, again, we have 20 times our sample size, which is 20 times 211. We have 211 upper class folks in our sample here. And that gives us 4220. How does that compare to, or I guess, what is our population here? Let's see if you're there with me. What is our population of interest in this example? Yes, exactly. People in the upper class. So how does 4,220 compare to all people that are in the upper class? Much less, right? So, Mike, we're all set, right? So less than all upper class, all people who are in the upper class. Good to go there again. So large enough. We want to make sure that n times p hat is bigger than or equal to 15, and n times 1 minus p hat is bigger than or equal to 15. So we haven't actually calculated p hat yet, but when we have the counts like this, we can kind of gloss over actually taking n times p hat and just figure out how many successes and how many failures we have. So we have 51 successes, which is bigger than 15 most days anyway. And we have 211 minus 51, which is 150 failures, which is bigger than 15 as well. I can't do math today, can I? 160. So again, the formula is n times p hat, but when they actually give us the numbers like they have here, you can kind of just use the counts instead of, you can use the number of successes that you have, which is given there directly, and see that we're good to go there. So each one of these things checks out and we're ready to roll. Any questions on the conditions or what I'm doing here? Is that all right so far? Okay. So conditions are good. We're ready to actually do some calculations here. So let's first figure out what our estimate is, what p hat is. Again, we have 51 smokers out of 211 upper class folks, which is 0.242. And let's just make a note that 1 minus p hat is 1 minus 0.242, which is 0.758. And then our formula is we're going to take p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. So maybe the quick thing to jot down here before we start plugging away here is what is my z star going to be? I think I heard a list over there, 1.645. Exactly right. So again, kind of back in that familiar world where we're in the z star, so it's finding the critical values is kind of like we did when we first looked at confidence intervals back in chapter 14. So z star here is going to be 1.645. Again, that's because we have 90% we want 90% confidence. So we can start plugging some things in here. This is 0.242 plus or minus 1.645 times the square root of 0.242 times 0.758 over 211. Again, formula is a little more complicated here, but not as bad as last chapter, right? So this is 0.242 plus or minus 0.049, which is, if you add and subtract, is 0.193 up to 0.291. So there's our confidence interval. Or am I done yet? No. What do I need to do? Interpret. Always make sure to interpret. So it's great that we just calculated that correctly, but we want to make sure to say what that means. So we can use our usual. The interpretation again is not going to change. Just kind of filling in what we're talking about and the new numbers here. So just like before, we'll say we are 90% confident that the true proportion of upper class smokers is between that interval there, so 0.193 and 0.291. So again, we're 90% confident that the true proportion of upper class smokers is between 0.193 and 0.291. So interpretation should feel pretty familiar there. And so that's it. So kind of same idea as what we did before, but now we're able to do this for a proportion. Any questions, comments you guys can think of on this example? Okay. Moving along then, quick conceptual question for you here. This also should sound familiar. So if I wanted instead a 99% confidence interval, would that be narrower than, as wide as, or wider than a 90% confidence interval? I think I'm hearing a few things a little louder. Wider, yes, exactly. And who can tell me why this will be wider? Yeah, Sarah? We're going to multiply by a bigger z star? Yes, exactly. So z star will be... So z star will be larger. What does that do? Why will that make it wider? How does that change the margin of error? Yeah, right. So larger z star means that my margin of error is also larger. So again, we've already I think talked about this question, but just to remind you that the same thing applies here. Sort of no difference when we're looking at proportions. The same ideas are going to be true. And then if you want to, I won't actually do the calculation, but the 99% confidence interval is 0.242 plus or minus 0.76. So the margin of error is larger. The confidence interval is going to cover more numbers there. Alrighty then. So that's our first way of calculating a confidence interval in this chapter. Actually, we're going to do something a little different in this chapter and introduce a second way to calculate a confidence interval. And this kind of gets at that idea that we sort of glossed over when we're looking at means, is that what happens if our conditions don't check out? And we sort of said, well, we'll just proceed with caution and do that interval anyway. So kind of the nice thing in this chapter is that if the large enough sample condition does not check out, then we have an alternative that we can do instead of just saying, well, let's throw up our hands and do it anyway. So again, if we do not satisfy the large enough condition, we can use this other method, which we're calling the +4 method, which will become clear in a minute here. And so that's where we're just adding 4 imaginary observations to our sample. So we're adding 2 successes and 2 failures. So we're just sort of increasing our sample size, which will change the sample proportion, but kind of you're just adding two failures, 2 successes. So it shouldn't throw things off too much. And then the idea is this helps to offset any skewness. Another issue I won't say a lot about, but if the large enough sample condition does not check out, you can sometimes get values in your confidence interval that are less than 0 or bigger than 1. So it's kind of trying to offset that idea too of having negative or values in your confidence interval that are bigger than 1. That's kind of, it doesn't make sense if you're talking about a proportion. So kind of the idea is going to be very similar to that very similar formula as we saw before. What we're calling our +4 estimate is this thing P with a little tilde on top of it. So this is P tilde. So we're changing the notation here so we know that this is different than P hat. And that's, again, kind of like we just said on the previous slide. We're taking the number of successes in the sample, adding on 2. And then we're taking the total number of things in our sample and adding on 4. So this is the 2 successes and 2 failures. And that's why we're calling this thing a +4 estimate. So again, if the hats, the tildes, if that doesn't help you, that's you're not required to use that. But again, it's kind of to make sure that we're very clear that we're using something different than P hat, which we were looking at before. So then our formula is going to look almost exactly the same, but we're putting in our different estimate here. So again, the setup here is, again, we have a simple random sample from a large population. To do our +4 confidence interval, we're going to kind of use this different estimate that we had on the previous page, P tilde, and then just throw that into the formula that we had from before. So instead of P hat plus or minus Z star times our standard error, it's now P tilde times plus or minus Z star times P tilde times all that stuff. Yeah.
Should we have n plus 4 on the denominator of the fraction?
Absolutely, we should. That is a typo in my slide. Thank you. There should be an n plus 4 in the denominator of the standard error. That's exactly right. All right, so this is our sort of our backup option here for a confidence interval. And we want to use this interval, another +4 there. Sort of our conditions here is we can use this thing when the confidence level, we want to make sure the confidence level is at least 90%, which is a small catch but not too serious. And then the good news here is that we can use this when our sample size is 10. So it doesn't matter what our counts of successes and failures are. As long as the sample size is at least 10, we can use this thing. And that should almost always be the case. If you have a sample of less than 10, that's really small. Okay, just a few quick notes. Again, we're talking about two methods here for a confidence interval. There's actually other ways. The textbook kind of has their recommendation. But what we can focus on in this class is we're only going to use this second interval that we're talking about here when our conditions for the first one don't check out. So kind of already said that, but just to remind you, if you're going through a homework problem, if it doesn't say calculate a +4 interval, it doesn't tell you what to do, default to the first thing we talked about, and then if the condition doesn't check out there, we can kind of have this as our backup option. So let's go ahead and do an example here where we need to use this interval. So here we're looking at political affiliation again. So here we take a random sample of independents, and thinking back to September, we find that 8 of them indicated that they would have supported a U.S. strike against Syria when that was going on. So here we want to calculate a 95% confidence interval for the proportion of independents who would have supported the attack on Syria back in September. Okay, so keeping your eyes on the instructions there, let's quickly jot down here. A good first step is what is a success? Is being an independent who supports a strike on Syria. So you can just kind of use that generic language, if that's kind of what we're interested in making a confidence interval for. And then, of course, our next step before we jump into calculations is checking our conditions. So do we have a random sample? Small enough random sample, small enough, large enough. Again, in interest of time, we'll kind of jump through these. Again, we're told it's a random sample. That's good. We take 20 times our sample size, which is 20 here, which is 400. Which is certainly less than all independents. So we're good to go on those first two conditions. But now our large enough sample condition for the first interval doesn't check out, right? We have 8 successes and 12 failures, both of which are less than 15. So kind of, whereas before we would have said, oh well, conditions don't check out, we need to proceed with caution and or not do this interval. We can use our backup here, but because n equals 20 is bigger than 10, we can use the +4 because our sample size is bigger than 10, we can use this second option that we have here. That's the good news. So that's kind of the motivation for having this second method here. So since our conditions check out for the second method, we're ready to roll. P tilde is going to be, again, we had 8 successes out of 20 people in our sample, so we're going to add 2 successes and add 4 total observations. 2 successes, 2 failures. And we get our estimate here is 10 over 24, which is 0.4167. Again, our formula looks very similar. It's P tilde plus or minus Z star times square root of P tilde times 1 minus P tilde over N plus 4. I seem to keep forgetting that plus 4. Don't forget the plus 4 in there. So quickly, let's say what is our Z star going to be here? Well, now we want a 95% confidence interval. Okay. So we want a 95% confidence interval. What's our Z star? And everybody said Check the table. Okay, it's been too long since the exam already, huh? Touche. Our z-star is going to be 1.96. We want a 95% confidence interval. We're going to use a 1.96 there. So we can plug our numbers in here and see what we get. So we're going to have 0.4167 plus or minus 1.96 times the square root of 0.4167 times 1 minus 0.4167 divided by 24. Decimal point there. Which is 0.4167 plus or minus 0.1972. Pretty large standard error there. Which is 0.22 up to 0.614. All right, and then of course our last step is to interpret. Interpretation again is essentially the same. We are 95% confident that the true proportion of independents who support a tag on Syria, who support is between 22%. Well, I've said proportion. Sorry, 0.22 and 0.614. So interpretation is exactly the same as it was before. We're 95% confident that the true proportion of independents who support an attack on Syria is between 0.22 and 0.614. So well, we're estimating that the proportion is somewhere between 20% and 60%. It's not that good, right? But at least we're putting some sort of a guess on what that thing might be. Any questions you guys can think of on what we're doing here? Is this feeling okay? All right. So now we can, man, I keep forgetting that +4 on there. We can start to fill out that table that we had, I think it was on the first page of this chapter. Or maybe it was the second page. It was the second page, I think. Is that in this case where we're trying to estimate the population proportion, we're halfway there, right? We know what our confidence interval formulas are. Again, assuming the conditions are okay, we can use these formulas. And we're ready to sort of forge ahead to find out what our test statistic is there. Does anybody have a guess on what the test statistic is going to be? It's going to be a Z, that's right. Any guess on what that form is going to look like? We're going to take our estimate, very good, P hat. That's all we know so far? All right, well, what's that? Minus the standard deviation? Oh, so remember for a mean, we had a t was equal to x bar minus mu naught divided by s over the square root of n. So we're actually going to talk about how we get this. I was just going to see, think about how our intuition translates this over. It's going to be the same idea. We're going to take our estimate. We're going to subtract off something that we hypothesize to be true, and then divide by a standard error. So we'll fill that in a little bit here. Before we do that, though, taking a quick pause on that idea, we want to go back to this idea of figuring out how to choose the sample size that will give us a particular margin of error. Sort of wrapping up confidence intervals for this chapter. So remember back to chapter, I think this was in 16 maybe, or one of those chapters, we looked at how we can find a sample size for estimating a population mean that will give us a certain margin of error, and it was on the test actually. We're going to have a similar thing here. So if we want to guess, if we want to say what our sample size needs to be for kind of in the planning stages of our study, if we are thinking about doing a survey or a poll and we want to estimate the true proportion within some margin of error, this is the formula that we can use. So our sample size n is going to be equal to z star divided by whatever that specified margin of error is. So this is our desired margin of error. And then I'm throwing more new notation at you here. I'm calling this thing p star times 1 minus p star. And I'm calling that thing a guessed value for the sample proportion. And maybe make a note here is that we'll talk about what this p star is a little bit more, but just to note that we always want to round. When you calculate m, always make sure to round it up. That'll give you a more conservative value there. So if your n that you end up with is 106.3, well, you can't have 0.3 of an individual. So always round that thing up. All right, so let's think a little bit more about what this p star is. In practice, this can be something that's either based on a pilot study or on some previous experience that's from a similar type of a study. So that's kind of, if you have some prior guess as to what your sample proportion might be close to, you can throw that in there for p star. Or if you have no information or you sort of don't have any idea what to guess there, you can just use 0.5. And again, that's going to kind of give us the most conservative. We're going to be more conservative if we use 0.5. It'll give us a larger sample size than we probably actually need there. So again, a little bit different here in that than we did in the previous chapter, in that we have to put in some sort of guess for what we think this might be. If you don't have any other information, just go ahead and use 0.5. Okay, so let's actually do this thing and see if we can apply this idea. So suppose we want to calculate a 95% confidence interval for the approval rating of Obama. We want to estimate that thing within plus or minus 3 percentage points. So kind of thinking about, I want to do a poll, or I want to do a survey to estimate this thing, and I want to make sure my answer is within plus or minus 3 percentage points. Assuming that I have no information, how many people should I sample in my poll here? So again, our formula, our n is going to be equal to z star divided by m times p star times 1 minus p star. So I need an m, I need a z star, and I need a p star. So my margin of error is 3 percentage points. So what's m going to be? So it's 3%, right? So I want that to be 0.03. That's a big thing there. Don't put a 3 in there. Put a 3%. So 0.03. Again, we just looked at this. My z star for a 95% confidence interval. 1.96. There we go. That's the enthusiasm I like to hear. And then again, if my p star, I'm saying I have no information available, sort of no prior information. I'm going to use a 0.5 there. I'm just going to guess that. Put that in there for my guess. So now I can plug these things in and get my do the calculation. So this is 1.96 divided by 0.03, and I've done another typo here. It should be a squared up there. So that thing squared times 0.5 times 1 minus 0.5. And if you enter that in, you'll get 1067.2 1, 1, 1. So that I actually need a sample size of equal to 1,068. So again, if I want my estimate of the approval rating to be within plus or minus 3 percentage points, I need to talk to 1,068 people. That's a lot of people. Questions or comments? You guys, any questions you can think of on this calculation? Is that all right? Yeah.
So you said you could also round up with P star. Or were you just talking about it?
I think I was just talking about n. Say it. Oh yeah. So
I mean,
it wasn't very clear. Yeah. So for this n, we want to round that up. Sorry, that's not clear at all. Thank you. So yeah, just don't round with the P star or anything, but when you get to the end, the final answer, round that number up, kind of like we did here. So instead of saying our sample size is 1,067.1, you can't have 0.1 of a person, so we'll round that up to 1068. Okay, so taking this one step further, suppose we actually do know what Obama's approval rating is. Other people are answering this question. So if you go to that website, you can look at the current approval rating. Right now we're sitting at 40%. So if we did that same calculation that we just did using this sort of separate information that we have, what do you think? How would the sample size we need change if we would have used P star 0.4 instead of P star of 0.5? How many think our estimated sample size would have decreased? Few hands. How many think it would have stayed the same? It's usually a bad answer, right? So how many think would increase? And the rest of you are not voting. That's fine. Well, again, so our n is equal to z star over m squared times p star times 1 minus p star. So it's not immediately obvious that that will decrease, right? Because that means this will be smaller, but this will be bigger. Right? So instead of 0.5 times 0.5, 0.4 times 0.6. The answer is actually decrease. So I'll sort of skip over the details. You can, if any of you have taken calculus, you can think about how you would show that that's true. But kind of that idea that if we don't have any information, we're going to use 0.5 will sort of give us the largest sample size that we will give us a larger sample size than we might actually need, but it'll make sure that we're within those 3 percentage points. All right, so that kind of wraps up confidence intervals, I think. Yep. And we want a quick talk now about doing hypothesis tests here for this chapter. So again, the setup is going to be exactly the same. We kind of have the same idea. We're just figuring out how we can apply this thing with a proportion instead of with a mean. So as we did before, we're going to kind of get our null and alternative hypotheses set up, and then we want to find out how unusual our results are, assuming that the null hypothesis is true. So usually the question that we're interested in is in the alternative hypothesis. So convention is we assume that the opposite of that is true, and then kind of figure out how unusual our results are if the null is true. And of course we judge unusual here by finding how many standard deviations we are away from the hypothesized proportion. So this is our test statistic. And then using that, how far away we are from what we hypothesized, we can find the probability associated with getting a result that's sort of as extreme as we have gotten, and that's our p-value. So we're going to be doing the same thing that we have done before, just again in a different context here. And then good news is we had two methods for confidence intervals. We only have one method for hypothesis tests. We're not going to worry about this +4 method when we're doing a hypothesis test. Okay, so here's coming back to that idea of that test statistic that we were thinking about just a moment ago. Sort of the setup is that if we have a random sample size n with an unknown proportion of successes, our null hypothesis is going to be that the true proportion p is equal to some hypothesized value p naught or p0. So this is p0 or p. So again, kind of we had mu 0 or mu naught there back in chapter 15, 18. Kind of the same idea. We're using that subscript of a 0 to denote that that's our hypothesized value there. So then this is going to be the formula for our test statistic. So again, thinking about when we had a mean, it was t x bar minus mu 0 divided by the standard deviation over the square root of n. We have the same idea here. We're taking our estimate, which is, so this is taking our estimate minus the hypothesized proportion, and then dividing it by something that looks like that standard error. Well, I'll just write. That looks like that standard error we had before, except a slight difference is that it's now p0 times 1 minus p0 in that denominator. So can anyone see if you guys can get this? Why do I have a p0 there in the denominator? Does anyone have an idea on that? Yeah.
Is it because you're assuming that P0 is true, so if you put a P cat in there, you would be assuming that the null hypothesis is true?
Exactly right, yes. So the comment was we have a p0 in there because of what the null hypothesis says, right? Remember our true standard deviation here was square root of p times 1 minus p over n. We didn't know what p was, so we threw a p hat in there. But here we're saying if the true proportion is really p0, then that's the value that would go in our standard deviation. So that's exactly right. Very good. Because we're assuming that p is equal to p0, we can put that into our standard error or standard deviation on the bottom there. So that's a tricky difference, but here is the formula that we're going to use here. Questions or comments on what we have there? So that's our test statistic. Again, the next thing we need to do is always figure out what our p-value is, and it's going to depend on what your alternative hypothesis is. So there's a nice chart of this in your notes there. If your alternative is greater than, again, it's going to be probability of being greater than your test statistic. Less than is probability of less than your statistic. And if you have a not equal to, then you kind of want to take both tails there. And just the two things to note here is, again, these inequality signs match up here. That's kind of the same thing we had before. And also we're back to having a probability involving a capital Z, which is this is our standard normal. It's our standard normal random variable there. So we're going to again use table A. Coming back to kind of that familiar case, we're finding probabilities involving that standard normal random variable. And then again, reminder that our conditions, again here, they're going to be slightly different than they were with the confidence interval. First two are going to stay the same again, but the last one changes slightly. Again, kind of that same idea of we're assuming that the true proportion is p0. So we want to use that p0 in our conditions to make sure that now our expected number of successes and our expected number of failures are each at least 10. So throwing some different things at you here, getting a little maybe seems a little ticky-tacky here, but again, when a confidence interval, we were using our the actual number of successes and failures that we got, and we're making sure those were 15. Here we want to make sure that our expected successes and failures are at least 10. And again, by expected, I mean if the true proportion really is p0, what would my expected successes and failures be? questions, comments on the conditions here? All right, well, let's actually get through, see if we can get through an example of this. So kind of going back to the first example we looked at, that first confidence interval we calculated this morning. Question we might want to know is, based on this survey, do we have significant evidence that the majority of persons from the upper class do not smoke? And we want to test this at alpha equal to 0.1. And so again, I think this is good practice. Maybe I think the wording in your homework problems can be a little less clear when you're looking at a proportion. So kind of if you cover up this sort of clarifying thing, it's not entirely obvious what we're trying to find here in that italicized question there. So to kind of help you start thinking about that, so what we want to test is we want to see if the proportion of non-smokers from the upper class is bigger than 0.5. So that would correspond to the majority of persons from the upper class. So a slight difference there. And let's quickly again jot down what a success is. Here we're looking at who can tell me what a success is? Kind of what's the group that I'm interested in saying something about? Yes, exactly. So we want upper class folks success is being upper class and a non-smoker. So in the confidence interval we were looking at smokers, and now we're kind of flipping things around here. And then let's try to set up what our null and our alternative hypotheses are here. So again, it's involving the proportion P. And again, my null hypothesis, I'm always going to assume that P is equal to something. So here I'm going to say it's actually equal to 0.5. What about my alternative hypothesis? What's that going to look like? Greater than, exactly. Because I want to know if the proportion of non-smokers is greater than 50%. All right, you guys are getting good with this. So let's continue here. So I want to check my conditions. Random sample, small enough and large enough. And I'm not going to rewrite these. These first two were checked previously. So we're okay with the small enough and the random sample. We do have a random sample, and we made sure we had a big enough population. But now our large enough, again, we want to do our expected counts. So we want to take n times p0 and n times 1 minus p0. Well, remember that we had 211 people in our sample. That's our n, and our hypothesized proportion is 0.5. Same for 1 minus p naught, 1 minus 0.5. And they actually give us the same thing here. This is this is 105.5, 105.5, and both of those are bigger than 10. So our large enough condition, we're okay because our expected counts are all set. Okay, so let's actually go about calculating our test statistic, p-value, all that good stuff. Actually, let me stay on this page. Again, p-hat is the number of upper class folks who do not smoke, so that's going to be 160 now out of 211, which is 0.7583. And then our test statistic here, calling that thing a z, it's going to be p-hat minus p0 times 1 square root of p0 times 1 minus p0 over n. Plug some things in here as 0.7583 minus 0.5 divided by 0.5 times 1 minus 0.5 over 211. If you punch that in your calculator, we get some really large number, 7.50. So kind of rushing through this a little bit, but just that P0, we're getting that. That's whatever's in your null hypothesis, kind of like we did before. So again, our z is 7.50. That's our test statistic. Our p-value is going to be a probability that a standard normal, and then something about 7.50. So which, if I draw a picture again here, here's 0. This is z. Out here is 7.50. Which area do I want as my p-value? Greater than, yes. So I want to know what this area is going to be my p-value. Picture not drawn to scale. And that's again because, so I want probability being bigger than 7.5, and that's again because my alternative was that p is greater than 0.5. So again, translating that thing down to figure out what my p-value is. And now you can use your favorite way of finding probabilities using the z table. I'll write down that this is 1 minus the probability of being less than 7.50. And again, if you try to look up 7.50 in the table, it's not there, right? So this is approximately equal to, since 7.50 is way off there to the right, probably being less than that is almost the entire area. So it's pretty much 1 is the area that's to the left of that 7.5. So my p-value is now approximately 0. So again, we're kind of back in the familiar case of calculating our p-values. It's a little easier. We're not using the table C anymore. We're not bounding the p-value. We can sort of say more exactly what it is. So then, sorry, we're just a little bit short on time here. Again, we want to compare this to our significance level, which is 0.01. So our p-value is less than 0.01. So what do we do? Reject the null, right? So because value is less than alpha, which is 0.01, we reject the null, and then we want to say what that means. And so again, our interpretations are going to sound very similar. So that means there is sufficient evidence to conclude, and then we want to say what our alternative hypothesis says. So to conclude that the true proportion of upper class non-smokers is bigger than 0.5. Or you could also phrase that to say there is evidence to conclude that the majority of upper class folks do not smoke. If you want to say it that way, is fine too. So again, because our p-value is really small, we're going to reject the null hypothesis, which means that there is sufficient evidence to conclude that the true proportion of upper class non-smokers is bigger than 0.5. So I'm out of time. I think that's the last thing I had to say up here. Just note that our table is now complete. We're all set with proportions. Thank you guys so much for being here. We'll see you guys on Wednesday. And don't forget, homework is due on next Thursday. But have a great weekend. Yeah.